Hello and welcome to Chapter 1, Sets and Logic. So what I have here is your textbook, and I simply highlight certain things that you want to make sure that you understand. So for example, we have the notation we use for sets. In other words, we can list the elements of a set, right? We could use this set builder notation where we say, B is a set of all x such that x is a positive even integer. Okay, that's how we would represent that collection of objects. So you want to read through your textbook and make sure that you understand the different notations, because they will be using them through the class. For example, we'll always use this z to represent the collection of integers, q for the rational numbers, etc., r for the real numbers. And there's other very, sort of less used notations that will come up. And for example, if you have the z and you put a little minus sign up here, the book will use that to denote the negative integers. So you want to become somewhat familiar with these notations. Some of the critical ones that will be used like regularly are the idea of this right here, the cardinality, or the size of a set. We use these brackets to indicate that. So yeah, for example, let's go down here. And we have the empty set is denoted. That's a set with no elements in it. Two sets x and y are equal, if they have the same elements. So essentially you can go through this if you like, and you can stop the video and take a look at the examples that are in the book. Like here's a good example. Let's show that these two sets are equal, right? Show that if A is equal to the set of all solutions of the equation x squared plus x minus 6 equals 0, and if B is a set that contains 2 and negative 3, we want to show that these two are equal. So what do we need to do? Well, essentially, the elements in B are listed right in front of us, so we have to find out if the set A contains the same number of same elements. So what do? Well, we solve the equation as you indicate here, or use the factor it or quadratic equation or whatever you would need to do. Or in fact, if you're just verifying that the two sets are equal, we can use the fact that we know there are at most two solutions to this, so we just check. And that's what they're doing here. They're plugging in 2 and realizing we get 0 here. Then they plug in, I don't like this notation, what they're saying here, but if we plug in negative 3, see it gets zeros also. So in fact, that indicates that these two sets are equal. So you'll have many exercises of this type that you may want to do to get familiar with how to show sets are equal. Let's see, what do I have highlighted here? Well, this is pretty clear, but I highlight it so that you make sure that you understand that for a set x to not equal a set y, written x is not equal to y, means that there must be something different about them, right? There must be at least one element in x that is not in y, or at least one element in y that is not in x, or both. Okay, so all right, more notation, and that's in this section they throw it in here sort of haphazardly. Suppose that x and y are sets. If every element of x is an element of y, then we use this notation right here. Right there, okay? All right, let's see what else we have. Here's another example. Okay, so for example, if I say let x be equal to this set of all solutions of the equation 3x squared minus x minus 2 is 0, if we want to show that x is not a subset of the integers, what does that mean? It just means let's find the solutions of this and see if one of them is not an integer. So if you go through that and if you solve for x, you obtain the solutions to this quadratic equation are x equals 1 and x equals minus 2/3, and 2/3 is not an integer, so that's enough to prove that the set of solutions x is not a subset of the integers. Okay, let's see, moving along here, let's see, what is this example? Oh, here's a really, we use a trivial example. Here's C is a set containing 1, 3, and A is a set containing 1, 2, 3, 4. Then C is a proper subset of A. What that means is that we use this notation here. It's smaller than A, and in fact, it is not equal to A. That's the notation that we would use for proper subset. So a very important object in mathematics is this thing called the power set of X. So what it is, so if you're given a set X, the power set of X is the set of all a set of all subsets of X. So for example, if A is equal to this set, then the members of the power set of A are, and I'll just go through this. So the empty set is a subset of A. The set containing A is a subset of A, etc., 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 etc. And one thing you may want to observe is that if you count them up, watch this, 1, 2, 3, 4, 5, 6, 7, 8, and that's 3. So it's not a coincidence that if you take 2 risen to the third power, you get A. So this power set is very important in the development of what is called naive set theory. And that's what I guess they illustrate that right here. Okay, let's see. Another important notation, which is basically just notation, is when we write down x minus y, that's the set of all things in x that are not in y. Okay, and let's see. And here's some calculations. You'll have some homework to make sure that you understand the notation. So if you have these two sets and you take their union, right? Well, you just throw everything into one big set. If you take their intersection, that's all the things that are common to them. Notice that the only element that is common is this, the set containing 5. So 5 is the intersection of the two sets. A minus B, so we look at the things that are in A that are not in B, you see that you get 1, 3, and B minus A is that. So you need to get familiar with how to calculate these things. So for example, Q, which that's a set of rational numbers, and R, the set of real numbers. Since Q is contained in R, then when we take the union, we get R, we take the intersection, we get Q, and we take Q, the things in Q minus the things in R. Well, since every element of Q is an element of the real numbers, their set difference is the empty set. Okay. So the set R minus Q, you may be familiar with, that's called the set of irrational numbers. Contains, things like square root of 2 and pi and e, and actually it's a much larger set in terms of cardinality than the set of integers, for example. It's a much larger set than the set of rational numbers, but I don't think we're going to get into that, what that means. By larger, I mean its cardinality is bigger. Okay, let's see what we have here. So if x and y are disjoint, what does that mean? That means they don't share any elements. So that means that x intersected with y is the empty set. Okay, this is kind of important. As it's an understatement. It is important to know what you're thinking about when you talk about a set X, like where does it live? And so this is called the universal set. Okay, so for example, let's take a look at this example. You'll see what I mean. So if A is the set 1, 2, and 5, that set that contains these three elements, and if U, the universal set, is specified as U is equal to this, right? So we have 1, 2, 3, 4, 5. Then this A bar, that's another thing that's indicated here, that's called the complement of A. So this thing here that you'll need to see, you'll see that quite a bit. The complement of the set A is going to be the things that are not in A, but are inside the view. And you can just see that that contains the elements 2 and 4, right? Now, if we would have chosen U differently, the universal set or the big set that we're thinking about that contains our set A, then the complement of A changes. So the complement of a set A is dependent upon the universal set that we choose. Venn diagrams. Okay, these can be useful when you're trying to sort of keep things straight, basically, in your mind. So what are Venn diagrams? So they look like this, right? And so they display the universal set is considered to be this, what's in this box, right? And where some confusion can occur is when you see these numbers. Like, for example, in this picture, what we're saying is region 1 is the set of all things that are outside of A union B, essentially, right? The universal set is everything. Region 2, that would be the set of elements that are in A and that are not in B, okay? Region 3, this little section right in here, that's the intersection of A and B, right? So here's some examples. Here, sometimes they're shaded, and this represents A union B. This represents A minus B. And then oftentimes you find convenience in using them in the following way. So here's a picture. Now, what do these numbers mean? Okay, so you don't, you have to be careful and make sure you understand what these numbers are representing. In this case, this is an example of a class or a college or that has a bunch of students, right? And the numbers you're seeing here are the number of students that are taking different subjects. For example, there are 34 students that are taking only calculus that are in that of these 3, psychology and computer science, right? So this is the calculus circle, psychology, I guess, circle, computer science circle, okay? So here's the sort of example. This picture is associated with this example right here, right? So it tells us among a group of 165 students, right, the whole universe, 8 are taking calculus, psychology, and computer science. That's where that 8 comes from right there, okay? It says 33 are taking calculus and computer science. Okay, so if you look at this, here's calculus, computer science. Well, we already have 8 accounted for in this intersection. So where are the other 25? Well, they're over here. So that is what enabled us, that information enabled us to put 25 there, right? So, et cetera, et cetera. In other words, it says here 33 are taking calculus and computer science. No, 33 are taking I made a mistake. So 8 are taking calculus and psychology and computer science. 33 are taking calculus and computer science. That's where the 25 came from. 20 are taking psychology, 20 are taking calculus and psychology. That's where that 12 comes from, right? 8 plus 12 is 20. 24 are taking psychology and computer science. That's where the 16 comes from, right? 70, it says 79 are taking calculus. Okay, well then to get to 79, we had to add another 34 up here, right? 83 are taking psychology. That's where this 47 came from, because you have to add up 47, 12, 8, and 16, and that, I hope, adds up to 83. Psychology, and 63 are taking computer science, and that's where this 14 comes from. So then after you're given all that information and you create this diagram, then you can answer the following question. How many are taking none of the 3 subjects? Well, I think without this picture, it'd be kind of difficult because, I mean, I don't know how you would do it, but I would have some like mental strain trying to figure out right? Without this information, how many are left over? Well, there's 9 left over. If you add up all those numbers and you subtract it from 165, or yes, then you're going to get 9. So that's the idea. Okay, the next idea, subject here, well, here is a theorem. Read through this theorem, make sure that you believe this. It's fairly straightforward. This is the associative law of unions and intersections, the commutative law of unions and intersections, distributive law of intersections and unions, and vice versa. Just think about these and make sure they kind of make sense, right? And the wording, associative, commutative, distributive, right? The identity law, you can see that there's a similarity between how sets behave in their unions and intersections and things like, addition and multiplication of numbers. So look at the similarities and see the differences and what it'll be enjoyable. Okay. All right, let me see what else we have. Okay, there's this idea of if you're given a collection of sets, right, you can take the union of all the things in that, of the union of all the sets that make up the set, and that's what this notation is. That basically, if you take the union of all the elements that you see here, you get, in each of those sets, you get this. So that's something cute. And similarly for intersection. And here's another, just be aware of these notations about if you're given S is this collection of sets, if you take the union of S, that means you're taking the union of all of the sets that make up S, okay? And you can do, there can be an infinite number of them as well, right? Okay, let's see. Okay, well, let's talk about Cartesian products. This is something that will come up quite a bit, and they just sort of slip it in there as an example, but we want to make sure we understand what Cartesian product of sets is. And essentially here, let's look at the example. You can read this to get the exact definitions and details, but here's an example. So if you have a set X and a set Y, then X cross Y, you just take each element from X and pair it up with the elements of Y. That's 1A, 1B, 2A, 2B, right? And then Y cross X is all the things in X cross Y, except you interchange the order, right? X cross X and Y cross Y. So, all right, there we have it. Oh, this is kind of an interesting example. So let's suppose we have this, we have ribs and nachos and shrimp, right? And French fries, those are the appetizers at some restaurant. And these are the entrees, chicken, beef, or trout, okay? So if you want to find out the number of all possible dinners where you choose one entree and one appetizer, well, you form the Cartesian, mathematically, you form the Cartesian product of the two sets, right? That's where you're choosing one of those. And if you count those up, you'll see that there's 12 possible dinners consisting of one appetizer and one entree. Okay, so that sums it up for chapter 1.1. Do your exercises and look at some examples and get comfortable with that information. So I hope this helps you. Thank you.